Hello, this is Ms. Nichols, and this is the first video in the waves unit, and the topic of the video is wave properties. The essential question for this video is, what is a wave and what properties do all waves share? And just a reminder that you're going to have some assignments associated with these videos, both to do your notes, notes checks, and also some little quizzes and things that will, you'll be able to use your notes. So please do have paper. Pause the video if you don't have paper, go get it. You can use the Cornell note paper we gave you in your packets, or you can use your own paper, but do please take notes as you watch. So when you hear the word wave, probably you have something in your mind, right? Most people have a good sense of what a wave is. But in general, the definition in terms of physics is that waves are energy moving through space. They're not actually made up of physical matter or mass. Waves are made up of energy. There are a few properties that all waves are going to share. The first is that every wave has some sort of wave source. There is something that is causing the beginning of that vibration or that jiggle that's going to be moving through the medium. And that brings us to our second thing that all waves have, which is known as the medium. The medium is the material that the wave is in. And I'll give you some examples of that in just a minute. But before we talk about them, I want to explain this definition just a little bit more. When you think about, this is like a slinky wave, right? A wave going through a slinky. And that little finger is pointing at a dot, a spot of that slinky. And you can see that that dot is going up and down, but it's not moving sideways with the wave, right? So the wave isn't the slinky moving through space. What is moving through space is the medium. Incidentally, the medium in this case would be the slinky because that's the material that the wave is in. So a few examples. A wave you all probably are familiar with in a swimming pool of some sort. The source of that water wave would be the awesome, spelled incorrectly, cannonball person that is jumping into the water. And the medium is going to be the water. So that wave is going to spread outwards from that cannonball through the water, and that wave wouldn't exist if you didn't have the person, right? There'd be no wave, and if you didn't have the water for it to move through, it wouldn't have a wave either. Second example. This is something that I have built. I have this in my classroom. I can't show it to you because we're not all live, but it's basically a whole bunch of gummy bears on the end of some skewers and then attached to a piece of duct tape down the middle. And it's really wonderful, majestic way of seeing a wave actually move through space. In this case, the wave source is the awesome physics dude's hand as he is jiggling that first gummy bear on one end of the material. And the medium is whatever kind of materials make up that concoction. So the medium in this case would be the gummy bears, the chopstick, and the tape mechanism that that person has created. So wave propagation refers to the direction that the wave pulse is jiggling compared to the direction that the pulse is moving through the medium. Two common examples of wave propagations are shown below. The first is called a transverse wave, and a transverse wave is defined as a wave in which the medium is vibrating perpendicular to the wave velocity. So in that wave you can see, right, the wave is clearly moving to the right, and if you look at one little piece of the slinky though, it's vibrating up and down, right? That slinky is jiggling up and down, and you can see that the wave velocity is perpendicular to the direction that the jiggles are jiggling. The other kind of wave shown is called a longitudinal wave. And in a longitudinal wave, the medium is actually vibrating parallel to the wave velocity. So in this case, the wave is moving to the right and the slinky is vibrating to the right and left, right, back and forth as it creates these little pulses of pressure that move through the medium. There's other kinds of wave propagations as well. One common one is called a Rayleigh wave. That's kind of like a circular motion that you see in oceans. There's a torsional wave, would be like that candy wave machine. There's a few other kinds of waves, but the most common waves are either transverse or longitudinal. Before we go much further into waves, we want to talk about some vocabulary about the parts of a wave. So if this is a picture of your typical transverse wave, we are going to define the crest of that wave as the tip top of each one of those wave pulses. So those blue locations shown are the crests. If you were talking about a longitudinal wave, it would be the areas where we have the highest pressure, where that medium is really close together. Second kind of part of a wave would be the trough, and the trough is sort of the opposite from the crest, right? It's the lowest point or the lowest pressure of a wave located at the bottom of each one of those little dips. And then the word amplitude, which is one you're going to hear a lot, is a really important one, is essentially the height of the wave, at least for a transverse wave. And it's measured from equilibrium, which is the location right in the middle of the wave. Another way to think about equilibrium is if the medium did not have a wave, if that string or slinky or whatever the picture is of down there didn't have a wave in it, it would be perfectly flat. That's equilibrium. And my amplitude will be basically the height of the wave measured up from that location, or it could be a negative number and measured down from the equilibrium. The last vocab word I want you to be familiar with is the word cycle, which maybe you've heard before in a math class before. But the word cycle refers to one complete wave. In other words, a whole crest and a whole trough. So this would be like one cycle crest and then trough. And then we have two more full cycles. So this picture shows 3 cycles. But a cycle can start from anywhere in the wave. So I could start the cycle right here, and I would have like half a crest and then a whole trough, and then I need another half a crest. So that would be one whole cycle there as well. So wave amplitude was mentioned briefly in the last slide, but it's really important because the wave amplitude is related to how much energy is in the wave pulse. It's really critical because waves are energy, and humans actually communicate by moving energy from one place to another. So understanding the wave amplitude is going to be a real focus in this unit. For example, low amplitude waves do not have a lot of energy, right? Like that baby splashing in the bathtub, compared to a high amplitude, which would be like a tsunami wave that would obviously have a lot more energy. Coming back to wave sources, which were mentioned earlier, wave sources are obviously a critical component of waves, and they can control a lot about the way the wave looks. Wave sources could create what's known as a wave pulse, which is like just a single crest or a single trough. Or wave sources can create periodic waves. Periodic waves means we have a whole bunch of cycles, a whole bunch of full waves back to back. So we either make a single pulse or we make a periodic wave where we keep on making the wave. And the picture shown above the top is just that single pulse of energy moving, and then the picture shown on the bottom shows the wave source making a periodic wave. Wave pulses, as we said, basically transmit a single burst of energy to one side or the other, and we can measure the amount of energy in the wave pulse by the amplitude measured from equilibrium. Positive pulses would be measured up from the equilibrium, so those are crests, basically, are positive pulses, and we could have a negative pulse, a negative amplitude, if we measured the depth, basically, of a trough. One other interesting kind of cool thing about wave pulses is that the shape of the wave pulse actually depends on the wave source. So we can make different shapes of waves. You probably think of most waves as having this kind of snake shape, but depending on the movement of the crest, you can actually make crazy shapes. You can make square waves or triangle waves or something called a sawtooth wave. So you imagine if I'm holding a slinky, if instead of just gently going up and down, I go really fast up and then I hold it and then I go really fast down, right? That's going to make a square wave as that wave kind of moves away from me through the medium. So if we were in class, we would make some different wave shapes so you guys could see what those look like. But for now, we've got the image of them below. Okay, so hopefully this gave you some new information, reviewed some information you maybe already knew, but the essential question was, what is a wave and what properties and vocab words are we going to use to describe and define waves throughout this unit? And just for fun, one of my very favorite Calvin and Hobbes comics. Thanks for watching.